some point of time in our life.
And come out.
I'm going to do reasoning in a slightly, in a somewhat abstract manner. But before I begin, I want to ask, yesterday we were talking about the distinction between inquiry-based learning and inquiry-oriented education. And the crucial distinction that we made was, here we use the pedagogy of inquiry tasks, but the goal is understanding. And not just understanding, but understanding of the syllabus, traditional. Oh, I have to use mine? Okay. I'm being soft. Okay. I wouldn't be able to use this. So I use. Okay. So that's inquiry-based education and inquiry-oriented education. The pedagogy, we do use inquiry tasks, as in this case, but we don't need to. We could also use other modes. For example, exposition is perfectly okay. It's kind of taboo here. The important part is the goal is not understanding. Understanding may come sideways, but inquiry abilities. That's the main distinction between these two guys. Now, I want to ask this question. Go back to the session that you just had on Sherlock Holmes. Does that have any place here? The session that you just had on Sherlock Holmes, will that fit here in inquiry-based learning? No, because it doesn't lead to understanding any of the curriculum syllabuses. Here, on the other hand, because you're looking at inquiry abilities, that has taken place. This is how, depending upon your goal, you will choose different things. And you will see these distinctions as we proceed more and more. Many of the things that we do here have no place here, which is why, if you insist on covering the syllabus, some of the most valuable things in inquiry will not take place, or will not take place in an effective manner. So one has to liberate oneself from that idea that we have to cover everything in the syllabus, in education at least. In coaching, yes. Okay. Another question, this is kind of introductory. Is it rational to believe that the sun goes around the earth and the earth is completely stationary? Is it rational to believe that the earth is completely stationary and the sun goes around the earth?
It is, yes.
It is or it is not? What do you say? It is rational. It is rational to believe that the earth is completely stationary.
Correct.
And the sun goes around the earth.
Correct.
Yeah. Everybody agrees? Yeah. But it is wrong, right? But no. The earth is completely stationary, the earth does not move, and the sun goes around the earth.
No, it depends on the evidences based on which we.
All the evidences we have, rational.
Based on what
From what we can observe right now, it's rational.
It is rational. Okay, so rational simply means, do we have good reasons to believe that, is the question. Depending upon the reasons, it may be rational or not rational. So rationality is not a matter of being correct. You can have conclusions that somebody considers to be wrong, but the conclusion may be completely rational. Okay, so let me give you an interesting case of this conclusion. So Martin Luther, this has to do with something that happened in the 16th century. this was a time when Copernicus was advancing the idea that the earth is not stationary, that the earth goes around the sun. And Martin Luther objected, saying this is just sheer nonsense. Okay. Why is this nonsense? Because in Joshua, in one chapter in the Bible, Joshua had some consultation with God, and after that, for some reason, I don't know exactly what, Joshua asked the sun to stand still. And when Joshua asked the sun to stand still, the sun did stand still. So Martin Luther's argument is this: if Joshua asked, but the Bible says Joshua asked the sun to stand still, and the sun stood still, had it been the case that the sun is not moving, it is the earth that is moving, would Joshua have asked the sun to stand still? Isn't that nonsense? Doesn't this fool know that this is said in the Bible? Okay, now if implicit in Martin Luther's argument is the idea that once Holy Scripture is a verbatim account of what God said, these are God's words. That's one assumption. The other assumption is God is infallible and will not tell a lie. If these three assumptions are given, then everything written in the Holy Scriptures is literal truth. It cannot be different. So anything that contradicts Holy Scriptures is false. Perfectly rational. What is problematic here is the assumptions that you're bringing into that what you have in Holy Scriptures is literal verbatim transcript of what God said. It is not human creation. The moment you say it is human creation, everything else falls down. Okay? But given those assumptions, the reasoning is perfectly legitimate, it's perfectly rational. You might object to the premises, but not to the rationality. Okay, so what I want to do is to go through that aspect. Suppose you get.
Yeah. So we are acquiring.
Oh, sorry. Yeah.
Yeah, we are acquiring certain inquiry abilities, right? By doing this reasoning, whatever that we are through inquiry. These abilities, why do we acquire, or why should children acquire? And what is the purpose of acquiring these abilities?
Okay, that's a more abstract question. So the way to get to a response to that question is to ask, why do we need education at all? What is the purpose of education? That's what I was talking about yesterday. So if you agree with me that the purpose of education is the well-being of humanity and the individual being educated, in some cases the well-being of humanity 50 years after the educator is dead, then we ask the question, what are the kinds of things that are needed for that? Right? And we come up with some answers. If the adult human beings have certain characteristics, then we will get to that well-being. And it follows then that education should help children acquire those abilities for the sake of that well-being. Now, if you assume that in order to have that well-being, you need certain moral capacities, let's call them moral sentiments, moral instincts. So one of the things that humans have is, when you see suffering, you try to do something about it. You are revolted by, for example, somebody torturing a cat. That's a natural human instinct. Most people have it, some people may not have it. So we'll say, okay, in which case we should nurture that instinct, the moral response. But that is not sufficient. You also need to think about the consequences of your actions. So somebody who has perfect moral response may still do something which is the same person would consider morally bad if only they knew the consequences of their action. That means you need to have moral reasoning. Right? So, which means that you should have reasoning capacity. And this would apply to other kinds of reasoning as well. So we can, this way, notice that I'm using reasoning to argue for reasoning. That's not quite legitimate, so I'm cheating, really. I cannot use rationality to argue for the value of rationality. That will be hopelessly sickly. You could say something like, you could respond by saying, I don't care about rationality, why are you arguing with me? So the very fact that you and I agree that rational debates are good means it is a good thing. Otherwise, you wouldn't buy my argument, right? Okay, so that will be one answer. The other is to say, let us assume that rationality is a good thing and proceed axiomatically, accepting it, and then proceed. If you and I agree that things like critical thinking, reasoning, rigor, inquiry, etc. are good things, understanding is a good thing, then let's proceed in a certain way accordingly. We could, of course, take it for granted that what is important is that everybody should obey the government. We're not. That obedience is a good quality, and we are saying obedience is not a good quality. So depending upon what your value system is, we will go into different ways.
No, you're saying let's save these sorts of questions for the evening.
Yes.
Back session and
Otherwise, I will go into something
we
completely
don't have
different.
much time.
Yeah, thank you. That is true. Yeah. Yeah. Okay, so I want to ask you this question. I'm going to give you fragmentary information. Okay. You have fragment of something, fragment of a living creature. Let me ask you, how many legs does it have? Hmm? No, you are getting only part of a picture. There is something else which is here, there is something more. And in this section that I am not allowing you to see, what is your conclusion? How many legs? 2 legs? 4? 2. Can it be 4? Where is that? That's a conclusion, right? I didn't give you that information. The only information I gave you was this part. From this information, how did you conclude that it has 2 legs? What's your reasoning?
Any creature with a beak like this has, I presume that is a beak.
Yes, this is a beak. Yeah. Regardless of my bad drawing, that's a beak.
And will have 2 legs.
Okay. So you're saying if a creature has a beak, then it has
It's likely to have
2
2
legs.
legs unless somebody has broken 1 leg.
Yeah. So unhurt, normal creature. We are ignoring all these other cases where one of the legs has been snipped off and so on. Yeah. Platypus? Yeah. How many legs does platypus have?
No.
I think it's, okay. I don't remember, I think it has 2. Yeah. Okay, so whether or not platypus, I can't remember whether platypus has 2 legs or 4, but we can look it up. Assume for the moment, for the sake of this discussion, that there is no such thing as platypus. Let's say this discussion is taking place in the 18th century, when people didn't know about platypus. Okay. What is the category of this bird? Again, you will say, if a creature has a beak, then it's a bird. The reverse, of course, doesn't. For example, then it means that the creature has wings, but if the creature has wings, it doesn't follow that it's a bird. So those are the kinds of things that you can conclude. But important is premise 1, and premise 2 is this creature has a beak. If these 2 statements are true, the third statement is unavoidable, namely, this creature has 2 legs. This is a general statement about creatures in general. This is a very specific statement about this particular creature we're looking at. This is also a very specific statement. And this, if these 2 things are true, then this has got to be true. This cannot be false. The conclusion is inescapable. So this is the nature of deductive reasoning. Whether the reasoning is deductive or not depends upon the way you formulate the premises. This is what is used in mathematics, typically, and certain aspects of science, but mathematics uses only this mode of reasoning. And a crucial part of this reasoning is that the first part, you're talking about the population of birds, and then the second statement talks about the sample. In this particular case, the sample has just one creature in it. And using these two, you are arriving at a conclusion about the sample. So we call this, let's say, population to sample reasoning. This is crucial to do this particular style of reasoning. There are forms of deductive reasoning where it doesn't have to be population, but I'm not going to do that for now. I want to contrast that with the reverse case. You are given information about a sample and you arrive at a conclusion about the population. Suppose, as you did earlier, you question this one. Right? Suppose you said, how do you know that every creature that has a beak has two legs? I'm not convinced. What will you do? If you believe that this is true, the conclusion follows. But suppose you believe that this is not true, then you have a responsibility to show that this is true. How will you show this is true?
Collect evidence.
Yeah.
Like you say.
You observe large number of creatures, right? So what you're going to do is to say, you collect a large sample, say randomly picked, okay? And then you notice that in every instance, a creature that has a beak has two legs. There are no instances in your sample of a creature that has a beak but not two legs. Now from that you conclude, therefore, in the population, you conclude this proposition is true. A state of affairs that you found in the sample, you now are moving that property as a property of the population. That reasoning is different from this one here. Why is this different? Because you have not really observed the entire population. There might be some bird somewhere or some particular species where that is not true. So let's say assume for the moment that for platypuses have a beak and they have four legs. I don't know if it is true or not, but it can be.
They have
Four.
They have four legs. Okay, nice. Yeah, so you may have looked at lots and lots of things, and people in the 18th century did conclude this is true, and it turns out that is not true because it wasn't included in the sample. And no matter how large the sample, this can happen. So classic example is the heart on the left case. 1 out of 16,000 people have heart on the right, perfectly normal people. So if you take a large sample of 1,000 human beings, you will not find somebody with heart on the right. So you might conclude that this is true of the population. Yet there might be someone in some place whose heart is on the left, and just happen that it is not in the sample. This is sample to population reasoning, which we will call induction. I'm defining the term induction to mean that when people say mathematical induction, that's not what they mean. They mean a particular kind of deduction. So that could be very confusing, so that terminology is separate. Mathematical induction actually is a particular form of deductive reasoning. The crucial part in this reasoning that I gave is you might be mistaken. You have not ruled out the possibility that there is some creature with a beak and 4 legs. When Jayashree said yesterday, in response to some of your arguments, I'm not happy with that argument. Remember? That was because Jayashree was in the field of mathematics. In the field of mathematics, this is illegitimate. You can't use it. You may observe 10,000 triangles, and you might show that all these triangles have 2 right angles as a sum. For the mathematician, that is not a valid argument, because you have not ruled out the possibility that there exists some triangle that you have not observed which has 3 right angles or 1 right angle. So mathematical reasoning has the following property. If the premises are true, there is no way of avoiding the conclusion. The conclusion cannot be wrong. Here, the premises can be true, and yet the conclusion can be false. Yeah.
The extrapolation that we did yesterday from single-digit numbers and the number of, is that a form of induction, which is deductive reasoning, that we did to say that we get
The number 11.
No, we went from the number of triangles.
Yes.
Is that induction?
That was induction. If I am assuming that we are referring to the same thing. So, for example, you said triangle has 3 sides, it has 2 right angles. A quadrilateral has 4 sides, it has 4 right angles. A pentagon has so much, and so on. We gave a large number of cases, and then now you conclude from that sample, you conclude this is true about the infinite polygons as well. That is inductive reasoning of this type, which is invalid in mathematics. It's okay in science. In fact, in science, there is no other way. You cannot give a deductive proof for the conclusion that every adult human being has exactly 1 heart. You cannot prove it mathematically, you can prove it only this way. So the conclusions in science lack the kind of certainty that math has. That doesn't mean that math is better and science is worse. The reason is this: mathematics says nothing about the world we live in. Therefore, mathematicians can afford to be completely certain by creating possible worlds and coming up with totally certain conclusions. Scientists, on the other hand, talk about this world, and we can't do that in this world. Okay? So, what you're trying to do is different in mathematics and in science.
And
Yeah.
it is called a scientific approach because science tends to use more induction and deductive reasoning in its work. Because yesterday we were saying this is a mathematical proof and this is a scientific proof.
Yeah.
We call it a scientific proof only because we are using a scientific tool, which is induction.
It is called scientific for 2 or 3 reasons. One reason is the grounds that are used in science are observation. When you want to prove something in science, you begin with observation. In math, if you want to prove something, the ultimate grounds are axioms and definitions. That is one crucial difference between the two. The mathematician doesn't care about observations when you prove something. Scientists, those are the grounds. The other is mathematics restricts itself to deductive reasoning, and science allows different forms of reasoning: induction, deduction, abduction, and so on. So there's a greater range of modes of reasoning that science permits. Math permits only one mode, deduction. So these are the 2 telltale distinctions between scientific and mathematical inquiries. And if you use that definition of science as a mode of inquiry in which grounds are observations, And the reasoning embraces deductive, inductive, abductive, etc. types of reasoning, then many of the things that we currently regard as not science will be science. So psychology will be a science, not a social science. A great deal of history will be science. And perhaps something like political science may not be a science. That depends. That we have to examine the nature of political science, so-called political science, to decide whether it is science or not.
By that definition, mathematics is not science.
Mathematics is not a science. So we have an Institute of Mathematical Sciences in Chennai, which by this definition is misguided. But then of course you can use words in your own way. You can define science differently so that math is also included. I don't know what that definition would be.
So maths is like a video game of real life.
Math is like a video game?
Of real life. Because all the laws, it seems to mimic real life in some of its ways. But all the laws are very predictable because it's within its own confines.
I'm not sure if that is the case. Math creates its own worlds and then arrives at laws governing those worlds. So many of those worlds may have no resemblance to real life.
Yeah.
It doesn't matter.
So it's creating its own world, that's why there is certainty in it.
Yes. Yeah. Because it does not make any claims about the world that we live in. Let me give you an example. Very telling example is in the, we talked about, did you talk about the fifth postulate yesterday, Justin? No, okay. There is something called the fifth postulate that Justin will deal with later. One of the formulations of the fifth postulate is, if you have a line and a point outside the line, you can draw exactly one parallel line to this. Euclid's what is called the fifth postulate, that is stated as an axiom, self-evident axiom. Everybody assumed it was true. In the 19th century, people started wondering, that doesn't look like a self-evident axiom, though they tried to prove it and they couldn't prove it. Then some people said, why don't we deny that axiom? Why don't we say no parallel line can be drawn? And some people said, we can draw many parallel lines. What will happen? They developed other forms of mathematics, geometry, not Euclidean geometry, but non-Euclidean geometries. So one of them was spherical geometry. So instead of Euclid's geometry is flat, this one is spherical, curved surfaces. And then the mathematicians got a little worried. So mathematician called Hilbert raised this question. We have these different geometries now. You have Euclidean geometry and many non-Euclidean geometries. But which geometry is true about this world, the world that we live in? That question is not a mathematical question, that's a scientific question. Because Hilbert was asking about this world. Had he been functioning as a mathematician, he would have said, we have created these worlds and such theorems are true about all these worlds. Do I care about which theory is true about this world? As a mathematician, Hilbert, not Hilbert, but Poincaré. Whenever I say Hilbert, I mean Poincaré. And Poincaré said, this world is Euclidean. He was making a statement as a pseudo-scientist, and he was wrong, because a few years later, Einstein showed that what is needed for this world is not Euclidean geometry, but spherical geometry, Riemannian geometry. So he was moving from the world of mathematics to this world. That's the distinction between the two modes of inquiry. And if you make that distinction, then the institute name in Chennai is mistaken. Okay. there was something that happened in the previous, the long legs and strides. I want to go back to that one. But before that, let me deal with abduction first. You might say something like, this is a theory of some sort. This is strictly speaking not a theory, but it's a generalization. The movement
How do you make this distinction
between,
theory and generalization?
give me a couple of days, I'll come back to that. Maybe let's ignore this for a minute. Even theory in quotes is actually not necessary. But I want to draw your attention to this one. Suppose you say if X is a mammal, then X is a horse. And Zeno is a mammal. I'm sorry. Let's make it real life. Yeah. The reasoning will follow without any problem when we cause confusion. So if I said if X is a horse, then X is a mammal, Zeno is a horse, then it follows that Zeno is a horse. Is a mammal. Mammals and horses are very different. Yeah. This is deductive logic. Conclusion is unavoidable. Suppose you reverse it. Suppose you say this, and then you say Zeno is a mammal. You cannot therefore conclude that Zeno is a horse. That would be bad reasoning. Now, logicians have a way of explaining why this is bad reasoning, because this is of the form P and this of the form Q. So in the first case, you're saying if P then Q, if P is true, Q is true, P is true, therefore Q is true. Perfectly good. Okay, you're moving in this direction, from P to Q. Suppose you say if P then Q, and Q, therefore P, and the logicians would say that is invalid reasoning. Notice that's what I've done here. You have reversed. First you went from P to Q. In this case, you're going from Q to P. Reverse case. In deductive reasoning, that move is completely invalid. In abduction, on the other hand, in the cases that Sripanna was talking about, something that looks very similar to this is perfectly valid. Why is it valid? Because the nature of the reasoning is different. So let me go back to the same examples. Fire causes smoke. This is your P and this is your Q. There is smoke. This is your Q. Okay? Now if you say, therefore, there is fire. Incidentally, this is an example found in most logic textbooks, in Nyaya logic, Jain logic, and Buddhist logic. It's almost like they have only one example, all these different logics. And I've been looking for more examples, I can't find them in textbooks. Anyway, so this looks as though this is invalid, right? Because you're going from Q to P, back. And in fact, there have been many people who are used to Western logic who say Indians are illogical people. But what happens here is not just P and Q, but this is the cause and this is the effect. and you are looking at the effect and reconstructing the cause. And the reasoning is not this simple. What it means to say, there is smoke, a smoke must have a cause. One possible candidate is fire, and in the absence of some other candidate, I will choose fire as a cause. And the most important part here is in the absence of some other candidate. And the demand that there must be a cause. In classical deductive logic, there is no requirement of causality. But here, you want causes. You want explanations. Okay? So this happens typically when you want a cause or an explanation. Here is something puzzling. Okay, when I bring two magnets together, under some conditions the magnets attract each other, but when you reverse, they repel each other. That's very puzzling. And I want an explanation. When I am puzzled, I want an explanation. First step. Second step, here is an explanation in terms of magnetism, North Pole, South Pole, etc., all those propositions. That theory of magnetism explains what I see. Now I look around, is there anybody else in the shop? This is the only theory that I can get. Therefore, because I'm looking for an explanation, I buy the best explanation possible. So these are two cases. What I described about this magnetism theory is not abduction. It is called speculative deduction. I'll come to that in a moment. But I'm simply trying to point out that what looks like an invalid move is not an invalid move if you're thinking about causes and explanations. Yeah.
In the earlier example where you said if X is a horse, then X is a mammal. If Y is a mammal, if I say Y could be a horse, then where do you fit this?
That depends upon exactly what you mean by could be. If you mean there is a higher probability, then of course it is wrong. But if you say something like it may or may not be a horse, yeah, but anything, I mean, that will be true. That's almost like a truism, right? There is, all that it's saying is that there is a possibility that it's a horse, or there is a possibility that it is not a horse.
Yeah, so it still falls under deductive reasoning.
Actually, it's an uninteresting piece of reasoning. Given anything, you could say X or not X. That's a tautology, right? You haven't arrived at any knowledge. So logicians would say that's a vacuous statement. A statement that will be true about everything by definition. Yeah.
Get this, can you please try and this you get?
Which part? The fire part?
Like, is this logical just?
Okay, the first point I made was, in deductive logic, if P is true, Q is true. And if you are given Q, you cannot conclude P. This is straightforward, right? However, here, it looks as though I'm using this. You can see that, right? I'm saying, if fire, then smoke. Smoke, therefore fire. That looks illogical. But if you understand that this is not simply a proposition, I'm saying this causes that, then things change, because along with the statement, fire causes smoke, and there is smoke, there is also an implicit idea that smoke must have an explanation. If you want to have an explanation, you look around and look for possible causes, and if you can, the only thing that you can find is fire, then you accept fire as the possible explanation and the best explanation, therefore fire, that there exists fire is true. Right? Let me give you another example that I tend to use quite often. This is also used in most discussions of abduction. And that goes like this. Whenever it rains, streets are wet. So here, what it means to say rain is the cause and wetness is the effect. Okay? And you were sleeping and you get up and look out and then you find that streets are wet. Okay? This is the effect. You observe the effect. And then you say, why are the streets wet? I'm puzzled. Because when I was asleep, the streets were not wet, now streets are wet. What caused it? Mathematicians don't worry about causes. The only candidate I can find is rain. Therefore, it must have rained. That's your first conclusion. But that statement, the way I've said this, is not quite rigorous. You have to say, unless there is contrary evidence, unless there is evidence to show that it did not rain, and unless I find some other explanation, I will buy this explanation. Okay. Now let's ask, what are the other possible causes for streets being wet? Of course, rain is one cause, but there is another cause. There is a truck, water truck that went on the street. So then you conclude, okay, this is something that you had earlier decided was true is not, that is no longer valid. A conclusion that was valid earlier, now in the absence, in the presence of a new theory, is no longer valid. Then you have to choose between these two theories. The rain theory and the truck, water truck theory. Do they make two different predictions? Can we think of a reason why something will choose between the two? If it is water truck, streets will be wet, but would it cause other things to be wet? But if it is rain, it will cause not only the streets, but also rooftops and grass and so on. Now you look around, if the other parts other than the streets are not wet, you will choose the rain theory. But if you find that rooftops and trees and grass are not wet, you will choose the water truck theory. So you're choosing between two competing explanations on the basis of further data. And that's how you do abduction.
Neha wants to say something. Also,
Yeah.
the time of the year and the location where we are staying. If it is summer, we won't predict that it would be rain.
If that's where the contradiction comes in, if you have a theory which says there cannot be rain in summer, then of course, obviously the claim that it rained contradicts that one. If it contradicts that one, there are two possibilities. One, your earlier theory is wrong, or your current proposal is wrong. Which one? Right? When there is a logical contradiction, there is always a possibility that you can throw out one of the two things. So you have to decide which one you want to throw out. Is this part so far clear? Okay, now I want to go to the next one, which is a little difficult. In abduction, what you have is, you have a particular observation. So for example, you are given two pieces of iron, and when you put them together, you find that they are coming together, but when you reverse it, they are moving away from each other. That is your observation about a particular set of a particular pair of iron rods. You have a theory of magnetism. How will you explain this? You have an interpretation. This is what you're postulating. The interpretation is that the two pieces of iron are magnets. You observe some particular phenomenon, individual phenomenon, not a general thing. You already have a theory. And within the theory, the theory allows you to say, this is legitimate within the theory. If you assume that, then the observation follows. Right? That is the nature of abduction. Abduction requires a theory, a particular observation, and an interpretation that explains the observation within the theory. Now, suppose you do this and I say, theory of magnetism, why should I believe that? Right? You are living, let us say, in the 7th century. And I say, what is this thing called magnets and north poles and south poles, attraction and repulsion? I don't buy any of that stuff. Then the game changes. The game changes. What is defended here is the interpretation. Now when somebody questions the theory, this is what you have to defend. So you begin with a number of observations and a large sample, and then you arrive at some observational generalizations through inductive reasoning. So you observe the behavior of magnets and you find that when you have some certain pieces of iron, when they are brought together, they attract, but when you reverse the direction, then they repel, whatever, repel meaning move away from each other. And then you construct an explanation, and the propositions of the explanation constitute the theory. And you say that the theory correctly predicts these, and therefore correctly explains these. I don't have a better theory, therefore I buy this. Here, what is defended is the theory. So in abduction, what is defended is an interpretation within a theory. In this reasoning, what is defended is the theory itself, and this is called speculative deduction. Okay, I will give you a written document that goes through these 4 modes of reasoning.
Can you define the contrast between these two and with the example of man?
How much time do I have?
8 minutes.
Okay, a contrast between?
These two with the example of man.
Yeah, notice that here you are assuming that magnetism is true, right? So for example, I have a pendulum at home which I'll bring tomorrow. It's a kind of base, a circular base, and there is a stand, okay, and then there is bases like this. Okay, and then you set this pendulum in motion. What you will expect is the pendulum will swing like this. What you find is when you set it in motion, it starts swinging like that, and then it starts swinging like this. Completely random motion, unpredictable motion. That's puzzling because you may expect butterflies to move like that, but not pendulums. So you have to explain it. How will you explain it? Well, I don't think this should have been explainable in the 12th century. They will be surprised, they will say there is some spirit inside the bob. But now you will, given your knowledge of the theory, you would say, okay, maybe there are some magnets inside the base, and maybe this is also a magnet. So what are the forces acting on this? These magnets, plus of course magnetism of this, plus gravity. So the combination of gravity and various magnetic fields will give you this result.
Depending the interpretation or the observation that I have.
Yeah, the observation is that this piece pendulum moves in random, unpredictable directions, which normally pendulums do not do, and that is puzzling. But the moment you know that what you have postulated, the interpretation is that there are other magnets inside the base, which you couldn't observe, but the theory allows you to do that. So this is an interpretation within the theory of magnetism and gravity. But that interpretation wasn't possible in the 12th century because the theory wasn't available. So in abduction, the crucial part is you must have a theory, well-defended theory, otherwise there is no abduction. And if the theory is false, then of course the interpretation is also false. Right? And in historical inquiry, quite often, in this kind of reasoning, you require the theory first, and then you can interpret the observation.
This example, look in that speculative.
Example of speculative deduction.
Same example. How would it?
Yeah, that will take some time. So it is there in the thing that I'm going to distribute to you if possible today, and then I'll get back to it in the later stage because I don't have the time to go through that.
So
And,
taking magnets always point towards north-south direction. Then
yeah,
there
all
also-
those things are observation generalizations that will defend the theory of magnetism. But we'll go through how to defend theories, maybe not just magnetism but also other things. For example, do you remember the summer-winter problem? If you look at the argument, okay, that's actually defending a theoretical proposal. The whole heliocentric stuff, we'll go through heliocentric theory, and that will give you some idea of what speculative deductive reasoning is. Yeah.
Speculative deduction and inductive reasoning are
Very different. If you read philosophy textbooks, sometimes textbooks give you use the word induction to everything that is not classical deduction. So they use the word induction to mean some sort of laundry bag of everything. They don't make these distinctions. So that's very confusing. In fact, they will use the word induction to refer to probabilistic deduction, to defeasible deduction. I haven't talked about those things. All of those which do not fit classical deduction. So that's not a useful concept.
Is the word interpretation of a theory, does it mean the same as an application, or is there
No, application, no, it's not quite the same. Yeah. In order to apply, you have to have interpretation. And application would mean, given the interpretation, what will be the prediction? So, for example, if you are asked a question, here is a cannonball with such and such velocity and such, whatever, initial velocity and direction and all that stuff and mass, what is your prediction? Where will it land? That is an application. So most exam questions are applications. Yeah. I don't think exam questions ask for abductive reasoning. I haven't seen one yet. Yeah. So exam questions don't test reasoning capacity except for the kind of reasoning that is needed for making calculations.
So how would I check interpretation in this case? I mean, the difference is not very clear to me right now. Application I can understand.
Yeah.
But what is an interpretation?
Interpretation here would mean you see something that calls for an explanation,
Okay.
and you draw upon an existing theory to explain it.
So the reason this is
Yeah.
happening is
And
what is in the theory.
yeah, and the interpretation that which gives you an explanation is within a theory. You are not defending a theory, you are taking the theory for granted. Yeah. And if you take some other theory, you will get a different interpretation and different explanation. Okay. We can continue this during tea time.
Now is the tea break.
Now is tea break. We will be here after 5:30.